Hello everybody, welcome to our fifth lecture on graphs. This is Professor Chakrabarti. I hope you have been able to understand the first four lectures that we have given. Today we start discussing a very important problem, that is the shortest path in a graph. The shortest path in a graph is a fundamental graph problem for which there are some very beautiful algorithms. And today that shall be the topic of our lecture. First, let us come to some definitions. The shortest path of a directed graph, and given two nodes in the graph called S and G, let us say start and goal, we are to find the shortest cost path from S to G. So this is our problem statement. Our problem statement is to find the shortest cost path from start to goal. Now, like in figure 1, in an unweighted graph, the edge costs that we have are considered to be all equal and are considered to be of cost 1. So here in figure 1, if we have our source node S as A and our goal node G as this G node, then the shortest path from S to G is from A to B to D to G. So if you see, this is the shortest length path. Though there are other paths, for example, there is another path which is there, and you can find that there is another path this way. So the other path this way has got more edges and is longer than this. Our objective is to find the shortest length path in an unweighted graph. On the other hand, if we have a graph like this in figure 2, which is weighted, that means there are weights on the edges, then the cost of the path is determined by the sum of the edge costs. For example, if we take this path from 1 to 2 and 2 to 5, the cost of this particular path is 2 plus 10, that is 12. So what is the shortest cost path from, let us say, node 1 to node 6 in this graph? You will notice that though the shortest length path from 1 to 6 is this, the cost of this shortest length path is 8 plus 1, 9. On the other hand, there is a longer path which is from 1 to 4, 4 to 7 and 7 to 6. This path is of cost 6, and therefore this path from the red colored path that we have mentioned is the shortest cost path. The goal of this lecture and the goal of our problem statement that we have given here is to find the shortest cost path in a directed graph. Now suppose we are given an undirected graph, then all we do is we replace the undirected edges by two directed edges. What we do is, if we are given an edge EMN as mentioned here, we replace it by two directed edges, one from M to N, the other from N to M. And the same weight is put on the two edges as the weight in the original undirected graph. Also, we have discussed earlier acyclic directed graphs. Therefore, the graph which does not have cycles is an acyclic directed graph. And we have already discussed a recursive algorithm for finding the shortest cost path, which was given as an exercise. Now, any graph traversal that we have done is of two kinds. Our basic graph traversal, as we have seen earlier, is depth first search. So we adapt depth first search to now find the path from S to G. So suppose we are to find the path from S to G, our recursive depth first traversal is path DFS from S to G. As earlier, we have our visited node which indicates whether a vertex is visited, a parent which indicates what is the parent of the node, and the successor function. So as before, which we have done, the first step is to mark visited, the node to be visited. Here is where we terminate. If we reach the goal, we terminate and go back through the parent links. If it is not the goal and we do not return, then for every successor which is not already visited, we mark the parent and recursively call the algorithm. So for example, if we do it on this example, the example in the top on this figure, then suppose we start from A, then we will call in the next one, we will call B and B is marked visited. From B we call C and C is marked visited. C may will calling E is marked visited. E may call D and D is marked visited. Then D calls G and G is marked visited. And then G is found to be goal by this step. And the algorithm terminates with this path. But as you will notice that this is not the shortest path. The shortest path is actually this path. And the DFS algorithm, if it has to now find the shortest length path, then it has to backtrack and look at all alternatives. And then there is a problem of loops, because if the graph has loops like here, then this DFS algorithm will fall into difficulty. So though the DFS algorithm is order V plus E, the current DFS algorithm that we have given here does not satisfy finding the minimum length path. We have discussed this earlier very briefly when we did traversal of graphs, and we said that the alternative to doing that is to do breadth first search. If you recall, breadth first search now uses a queue, and therefore in breadth first search what we do is we now have a queue, and this queue initially consists of the start node S. So the beginning of the queue we have the start node S, and visited all nodes which are initialized, visited are initialized to 0. Then we go on to this main loop of this program. The main loop is as follows. This is the main loop. This main loop executes as follows. The main loop starts and continues till while it will continue if so long as this is null. If Q is empty, which means that we will have no path. So at any point in time, if Q becomes empty, while we have checked here, if it even comes out as Q is empty, so here if we end up with Q as null, then we are failing. Which means that there is no path. If Q is not null, we remove the first element from the queue. We check whether it is a goal node or not. If it is a goal node, we terminate the algorithm here and return with the parent links. The breadth first search, like the depth first search, stops as soon as we get the first goal node. If it is not a goal node, we mark the node to be visited. Once we mark the node to be visited, then for every successor, every element k, which is a successor node, for each successor of the node which has been dequeued, which is n, we check whether that new successor k has visited 0, which means that it has never been examined before, or if it has been examined before, it is not already in the queue. If that is the case, which means that if it has not been taken out of the queue, visited is 1 when it is taken out of the queue, and secondly, it is not in the queue. That means a new node has been seen. This part means a new node has been seen. Once a new node is seen, we mark the parent, we increment the length by 1 and we put it into the queue. So there are two cases which does not satisfy here. One is if it is already visited, we do nothing. Secondly, if it is not visited but it is already in the queue, then also we do nothing. So we will discuss all these issues. First, let us work out this on the same example that we had here. So our start is S and our goal is G. As per the algorithm, A is our start node and capital G is our goal node. So as per the algorithm, what we do is we initialize the queue to A and then we take an element out of the queue and we dequeue it. The length of A is 0 because all lengths are initialized to 0. Then once A is removed, then A has only one successor, B. B is put into the queue. So now the queue contains B. Then B is removed from the queue and marked visited. Once B is marked visited, B has got children C, D and F. So C, D and F are put into the queue. And each of them, so if this A was length 1, then B became length 2 by this step. C, D and E, F all have length 3. So C, D and F, A had 0, B had 1, we started with 0, and each of this have 2. So C, D and F have length 2. So C is removed because it is in the beginning of the queue. So C is removed. It is marked visited. All those nodes which are dequeued are marked visited. Once C is removed, then C has got two children, E and H. And E and H are put into the queue and the length of E and H are 3 each. Now the queue contains D, F, E, H. D being the beginning, D is taken out of the queue. Once D is taken out of the queue, then in the queue we now put G. So G is put at the end of the queue and G has got length 3. So now we have the queue of F, E, H, G. Next we remove F. So F is removed out of the queue. F is this one. F has got two children. One is B, which is already marked visited. The other is D, which is already marked visited. So in this case, since both the children are marked visited, nothing happens. So the queue now becomes EHG. Once the queue becomes EHG, then E is removed from the queue. Once E is removed from the queue, then E has got children K. And K is of length 4. K is a new node, it is neither visited nor in the queue. So E is removed and K is put into the queue. Now H is removed from the queue. H has got no successors, so nothing happens. So after that only G and K remain. So K is there, G is removed, G is a goal node, and once G is a goal node, we therefore terminate the algorithm here. So what we now need to do is we can now prove that first the length value that we compute here, is always the shortest path from S to K. I leave it to you to prove by induction. Firstly, it may be easier for you to prove this step that when a goal node is removed from the queue, the shortest path has already been obtained to it. As we have seen in this example in the breadth first search, you can prove by a simple induction that whenever a goal node is removed, the shortest path is obtained. And if a node is already visited and is already in the queue, then its proper length is already computed. So this algorithm, while it works like V plus E, unlike depth first search, which need not guarantee the first solution to be optimal, this algorithm will guarantee that the first solution that you get is the minimum length solution. The only thing in this code is that this piece may actually probably be put right at the end if queue becomes empty, because if you come out with queue empty, you actually fail. So this, if this is not empty, if this is empty, it won't enter to check this. So now, after having done this, we now come to weighted directed graphs. In weighted directed graphs, there are weights on the edges. So in each of these 4 graphs in these 4 figures, there, as you can see, figure 1, which is an acyclic directed acyclic graph. This is a DAG. Figure 2 is a general graph, G, but it has got positive cost edges, but it can have cycles. So positive cost edges are something which are realistic. In many cases, most of the edges are of positive cost. But in the more general case, as in figure 3, you can have negative cost edges like this, or this, or this, and so on and so forth. And negative cost edges introduces a new dimension to the problem. But this is in figure 3, it is more general than figure 2. It has got negative cost edges, but it does not have a negative cost cycle. In figure 4, we show what is the concept of a negative cost cycle. Here, this cycle has got a total cycle cost. This is -8, and these two add up to 5. So there is a negative cost of 3 on this, which means that this is a non-terminating cycle. So we actually do not consider those problems where there is a negative cost cycle. So we have got 4 major kinds of graphs. One is a directed acyclic graph, which can have positive and negative edge costs. The general graphs with positive costs only. General graphs with no negative cycles and negative cost cycles. So we will, in this lecture, we will consider only item 1 and 2. We will leave 3 as an exercise for all of you to work out. So now let us see how the algorithms proceed for 1 and 2. Actually, in the previous lecture on traversal of directed graphs, we have discussed the shortest cost path in a directed acyclic graph. And we took the same example that we have shown in this figure. We then discussed the recursive. First, we discussed, as in our algorithmal design strategy, we discussed a recursive algorithm. And this recursive algorithm says a shortest path from n to g. The cost of that path is 0 if n is equal to g. The cost of the path is infinity if n is not equal to g and n has no successors. That means it is a terminal node like this. It is a terminal node like this. This node has got no successors. Since this node has got no successors, from this node we will return this node. If it is a goal node, it is 0. But if there was any other node like this, which is a non-goal node, and it is a terminal node, then it will return infinity. If this was a goal node, then it will return 0. That is why this is first it is a non-goal node and successors is null, it returns infinity. Otherwise, we look at all the successors m of n and recursively find out the cost from m to g, add the edge cost from n to m, and find the minimum for all m. So if the successors are not empty and n is not equal to g, we recursively find out. So this is our recursive definition. How do we translate that into an algorithm? We again maintain our three visited. We maintain a new cost, which is the cost from I to g. At every node I, we maintain a cost value from I to g. We initialize it to infinity. The successor function remains. So the DFS implementation of this, we have a local variable which we will use to compute this minimum here. So as soon as we enter, we mark a node visited. If a node is equal to g, then the cost is 0 and we return 0. And therefore, we mark the cost 0 for that node because cost of g to g is 0 and return 0. Otherwise, for every successor of that node, if it is not visited, we recursively visit it. And when we come out of it, we know what is the value that we get. Okay? And once the value that we get out of this, which is the value of DFS n, will be stored, as we said, in cost n. Cost n will contain the shortest cost path from n to g. Then for that n in this loop, we add the edge cost from node to n, add it to cost of n, which has now been computed, and minimum with the value, which in this loop, when it comes out of this loop, value contains the minimum of this plus of these two values, the minimum of these two values for all successors for each n, which is the successor of node. So as soon as we get it, we return this. So by this recursive algorithm, we see, so let us see how we are getting this computed. The algorithm, if S is the start and G is the goal, the algorithm will visit this node, then come here, then come here, then come here, then come here. This returns 0. All the elements marked in red are the values that are returned. It comes here, it comes back here, then it calls this node, then this calls this returns 0. 0 plus 4 gives this value 4. Now this value, when it comes back, is the minimum of 3 and 4 plus 4, 8. So this value is 3. Similarly, the algorithm then backtracks here, gets this, and it is not difficult for you to see that all these values will be computed as the red values are indicated here. This algorithm visits a node only once, looks at all the successors, and therefore the time complexity of this algorithm is order v plus e. Obviously, it is a DAG, so it does not work for graphs with cycles. You try this algorithm on graphs with cycles, and you will have the same problem that we saw earlier in the depth first search for an ordinary graph. However, it works for negative edge costs because there are no cycles in this graph. And it can be adapted for the all pair shortest path in a DAG, which I leave in as an exercise. That means, given a graph, if you are to find the shortest path between every pair of nodes, what I forgot to mention a little earlier is that in the type of graph problems that we have, we have a problem which we are now doing is the single source goal problem. Given S and G, find the problem. Second is single source given S, find the shortest path to all other nodes. And the third is the all pair shortest path, that I find shortest path between every ij pair. So here I am asking you to find the shortest path between every ij pair. This I am leaving as an exercise. Now we come to the second case where we find the best first search, we find the shortest path in a weighted directed graph where we assume that the edge costs are positive. What we will do is we will adapt breadth first search. But since there are costs on the edges and therefore every node has a cost of reaching that node, we now define a new value in the algorithm called cost j. Whereas the cost j in the previous DAG algorithm was the cost from j to goal, here being breadth first search, it is the cost from S to j. And it is initialized to infinity for everybody. Then what we do is we try to determine this cost, and in breadth first search, while we were maintaining a queue, here we will maintain what is called an ordered queue, which is ordered by cost. This ordered queue is ordered by cost value. Here again, this part, if we come here, we will check, we'll modify this as before. So the breadth first search will now be modified to best first search, where instead of removing the first element of the queue, we will remove the node in that first element in the ordered queue. That means the queue is ordered by cost, so the minimum cost node in that ordered queue will be removed. So what we do is, this part of the code, because the while loop enters this way, this part of the code actually comes here. That if we come out of this while loop, if we come out of this while loop when ORQ is empty, then we will say there is no solution. The first thing we do is we remove the minimum cost element from Q. Instead of removing the first element of Q, the first element of Q with this Q being ordered, the first element of Q is the minimum cost element. Again, we mark it visited. Again, like in breadth first search, if that is goal, we terminate with cost of that node. So if we remove J and J is goal, we terminate. Otherwise, what do we do? For each successor of J, we check if it is already visited. If it is already visited, we do nothing. On the other hand, if it is not visited, in breadth first search, there were two cases. It was already in the queue, it was not in the queue. If it is not in the queue, it is fine. The same thing applies here. If it is already in the queue, in breadth first search, it could not have come with a smaller cost. But here, as we have seen, you have a shorter length path. Maybe there is a shorter length path, but that shorter length path is not necessarily the shorter cost path. So you could come back to an existing node in the ordered queue with smaller cost. So we now check if the node is not visited, if it is a new node, its cost j was initialized to infinity. So cost k, which was initialized to infinity, will now be cost j plus cost j, edge cost jk. On the other hand, if the earlier cost was larger, then you update the cost. So this is what is called a cost update step. And if the cost is updated, if the element is newly inserted, then you insert in the queue. If the cost is updated, you reorder in the queue. So the modification from breadth first search to best first search is as follows. The summary is that we maintain an ordered queue by costs. We remove the minimum element of queue. We mark it visited. If it is already a goal node, we terminate. If it is not already a goal node, then we generate its successors. We check whether the successors are already visited. If a successor is already visited, we do nothing. If a successor is not visited, then it may be a new node, then its cost is assigned and it's inserted in the queue. It may be an existing node whose cost is updated by a lower value, and then we again reorder it in the queue. This is a famous algorithm, and it goes by various variants and versions and implementations. But overall, in the computer science graph algorithms community, it is most famously called the Dijkstra's shortest path algorithm. Let us now see how we will execute this algorithm in this figure 1. In figure 1, we are to find the shortest path from S to G, where S is node 1 and G is node 6. So how does the algorithm proceed? Initially, the queue is marked with S and cost of S is made 0. So it has got node 1, its cost is 0. This node is removed. Node 1 has got 3 successors, node 2, node 4. No, it has got 2 successors, node 2 and node 4. For node 2, its cost is 2. For node 4, for node 2, its cost is 2. For node 4, its cost is 1. Therefore, in the ordered queue, you will have node 4 with cost 1 and node 2 with cost 2. So in the ordered queue, 4 is in the beginning. So node 4 is removed. It is marked visited. As before, those nodes which are removed are marked visited. Now 4 has got 3 children. So 4 is removed and marked visited. It has got a child 3. The edge cost being 2, the cost to node 3 will become 3. It has got another child 6, whose edge cost being 8. So total cost of node 6 will be 9. And then it has got node 7, and therefore the cost of node 7 will be 4 will be added, so the cost of node 7 will be 5. So the node 2 existed, node 3 was added of cost 3, node 5 was added, node 5 is another successor of node 4, so node 5 is of cost 3, so node 5 is added of cost 3, node 7 of cost 5 and node 6 of cost 9. Because node 4, as you can see, has got 4 children, 3, 6, 7 and 5. So 4 of these children are added. Now, and 2 was already there, node 2. Now in the beginning of the queue, node 2 has got the smallest weight. So node 2 is removed from and marked visited. Once node 2 is marked visited, then node 2 has got only 2 children. One is node 4 and one is node 5. Now if you note that both node 4, this node 4 is already visited. So by this algorithm, this part does not address node 4 because node 4 is already visited. On the other hand, node 5 is not visited, but it is in the ordered queue, but it is there with cost 3. Since it is there with cost 3 and it now comes with a larger cost, which is 2 plus 10, 12, therefore this part does not get executed. So this step not getting executed, there is no change in any of the values and only node 4 remains, and this is the queue remaining. Then the next element in the ordered queue is 3. 3 is removed, marked visited. Then when 3 is removed, it has got one child 1 and it has got another child 6. Now there are very interesting things. The node 1 has cost 0 and it has now come with a node cost of 3 plus 4, 7. So nothing happens to node 1 because it is already visited. On the other hand, to node 6, node 3 was of cost 3 and this edge is of edge cost 5. Therefore, now we have come to node 6 with a cost of 8. Node 6 already had a value of cost of 9. So this step, this condition gets invoked, and therefore this is the cost update stage and node 6 is reordered in the queue. Once node 6 is reordered in the queue, in the next step, queue becomes like this and node 5 is removed and marked visited. Now node 5 is removed and marked visited. Node 5 has got one child, which is node 7. And it comes to this node 7 with a cost 5, which was 3 and 6, 8. But node 7 already has a cost 5. So this step does not get executed and therefore there is no cost update. Therefore now we have two costs. Node 7 of cost 5 in the queue and node 6 of cost 8 in the queue. So node 7 of cost 5 is now visited, and once node 7 is visited, it has got a child of node 6, and now we come to node 6 with smaller cost, and therefore using the cost update step here, node 6 cost is updated. Now node 6 is the first remaining element of queue. Once we remove node 6 being the goal node, the algorithm terminates with cost 6. As you can see from this algorithm, the first time that we have terminated is that we have terminated with minimum cost solution. Therefore, whenever a node, the first theorem which is of most important consequence here is that whenever a node is removed from the ordered queue, the best cost path to that node has already been obtained. It is done in 3 steps. One is whenever a new node, whenever a new node is generated, we get its cost. Whenever a node is already existing in the ordered queue and we come to it with a smaller cost, we update the cost in this cost update step. And the third thing we do is we remove the minimum node from open. So let us say by contradictory argument that this is not true. If this is not true, then there is a shorter path to a particular node n. If there is a shorter path to a particular node n, then the ancestor of that node with the edge costs being positive, this was the typical criteria. If the edge costs are positive, then in the ordered queue, there will be an ancestor to this node, its parent or parent to parent or somebody. And since the edge costs are positive, that will be in the ordered queue. If that is in the ordered queue, then no node of cost greater than that will be removed because we are removing the minimum node. So you can prove by contradiction that this algorithm will guarantee that whenever a node is removed from the ordered queue, the best cost solution has been obtained. Therefore, whenever the goal node is removed, the best cost is obtained. Only one change you have to make in the algorithm that I have provided here is that this termination will come at the end. When you come out of the loop and the ordered queue is empty and you have not terminated, then you terminate. And you have not terminated with the solution cost, then you terminate. So please make that change. So how do you implement this algorithm? we will simply implement it by any data structure that requires us to insert, reorder. Reorder is an equivalent of delete and insert, and remove min. So any balanced tree data structure or a min heap data structure which has got the insert, the reorder is equivalent to delete and insert, and a min removal, and each of them takes order n steps. We do it for every edge at most once. Therefore, it is an order E log E algorithm, and log E being log V squared is also an E log V algorithm. You can also implement it using arrays where this removal step will take order V time, that each of this step will take order V time, and we will have to at most remove V number of nodes. As we have seen, we had to remove every node, and this was the 6 was the last node that we had to remove in this case. Therefore, it will be order V squared or E, whichever is the larger of the two. So this algorithm can also be executed in order V squared plus E time, either V squared or E plus E time, whichever is the larger of the two. In dense graphs, it is better probably to use this algorithm, but in general the number of nodes edges is much less than V squared. Therefore, this is there. And if you use other more deeper data structures like Fibonacci heaps, then you can do it in order V log V time as well. We leave that as an exercise. The question is that if there are negative costs, but no negative cycles obviously, then this proof does not hold. Therefore, the steps in this algorithm where we have said if visited is equal to 0, we don't do anything, this part will have to be revisited. And therefore, there is a chance of an already visited node may need to be revisited. So this change has to be put into the algorithm. The complexity of the algorithm completely changes. I leave it as a homework exercise for you to work out. Thank you very much. We have discussed one of the most important algorithms of graphs, which is to find shortest paths. We have seen that there is a recursive definition. This recursive definition can work both ways, from start to goal or backwards from goal to start. Depending on whether we are using depth first search like in directed acyclic graphs, we use a depth first search where we compute it from goal to start and recursively compute it through depth first search. On the other hand, the recursion can be solved by breadth first search, but if there are costs on the algorithm on the edges, then these costs have to be ordered. Therefore, it becomes what is called the best first search or the Dijkstra's algorithm. Thank you very much.